This is Steve Edford. I want to talk about one of my favorite subjects, that's quantum gravity. That's an alternative to general relativity, which of course I'll show later that general relativity can't cause gravity anyway. But anyway, in a nutshell, this is what quantum gravity gravity is equal to the summation of the nuclear bond of each and every pair of adjacent atoms in a body. Now that could be quite a bit. Of course, now they'd say, well, the nuclear bond, it's a very weak force. Well, but if you take enough of them, it adds up to a substantial force. Because I looked up on the internet, and the Earth is made up of about 1.33 times 10 to the 50 atoms. I mean, it's, rough calculation. So that would be, and it would be actually a little more than that, because if you take one atom in the middle of a body, it's going to have like at least 10 adjacent atoms around it. So there's 10 right there for that one atom. Now the next atom to it, it's going to have 10 around it, but one's already counted, so it's going to be 9. So maybe roughly about 9 times the number of atoms in a body. So anyway, since the nuclear bond is so weak, well, if you take just a tiny ant, like one ant by itself probably can't lift up a bottle cap and carry it on its own, even though ants are very strong for their weight. But if you take about 10 ants, they could probably pick up, if they could work together, they could carry that bottle cap. So now if you take about 1,000,000 ants, if you could harness the power of 1,000,000 ants, they could probably pick up your car and move it because you have enough of them together. So anyway, that's the way it is with gravity, that you take enough nuclear bonds and you add them all together, then you get quite a substantial force. So anyway, what made me think about this is I was thinking about the difference between a star and a black hole that it collapses into. Because with a star, you have X amount of mass and it produces Y amount of gravity, what you would expect. But now with a black hole, you still have approximately X amount of mass, but it produces far, far more than Y amount of gravity. So you have to wonder, why is that? Why does a black hole produce so much more gravity? Because it's the same amount of mass. Even Isaac Newton's law of gravity doesn't cover that one, and I'll bet relativity doesn't either. I don't know about that, but I bet it doesn't. But anyway, I was looking at the difference between the two. One of the obvious differences is the size. A typical star might be about 1,000,000 miles diameter, and a typical black hole might be about 10 miles diameter. At least that's the number I've heard thrown out there before. So okay, that's a reduction factor of 100,000 to 1. So now if you picture a string of atoms, a straight line of atoms across the diameter of a star, it's 1,000,000 miles long. That's X number of atoms. Now when you compress that star down to the size of a black hole, now this same string of atoms, same number of atoms, it's only 10 miles long now. So now if you take the distance between two atoms, if there are 100,000 units of length distance between each other, now when they're in a black hole, they're squeezed down to where there's only one unit of distance between them. So they're a whole lot closer. So I looked at it like, how does that have anything to do with gravity? So I picture it, if you take, well, I got some diagrams here. If you take Isaac Newton's laws of gravity, which is you have force gravity is equal to G, universal constant for gravity, times N1 times N2 over R squared. That gives you gravity. Now this is your typical diagram for it, mass 1, mass 2, and the distance between them. So now if you take that same mechanism and apply it to a pair of adjacent atoms, and you might wonder, why would you do that? Well, it's just for illustration. Because now what you find out is that these two atoms that were a significant distance apart like this, now when you smash those atoms together, like in a black hole, they're all pressed so much closer together. It reduces R by a factor of 100,000 to 1. So when you look at the R squared, because gravity is inversely proportional to the square of the distance. So now you take that 100,000 squared, now you end up with 10 billion. So, Anyway, I came up with an equation that this is what you could do to Newton's law of gravity to modify it, because you introduce two numbers, d1 and d2. It's a mass density coefficient for mass 1 and for mass 2. Then you could make this work out so that Newton's equation for gravity for a black hole would actually work. Because the force of gravity between a black hole and a normal planet, the d1 would be 10 billion times the mass of the black hole. And then d2 would be 1, because normal matter has a mass density coefficient of 1. That's why we've never missed it before in Newton's law of gravity. But now if you introduce this mass density, so now if you picture, if this is two black holes, this is 10 billion times the mass of the first black hole times 10 billion times the mass of the second black hole. Now you've got super duper gravity now, because it's 10 billion squared increase of gravity. And now I figure there's two models of how you could do it. Two typical atoms, you bring them together to where the electrons and protons are just interfering with one another. Or a second model of it is you might be able to compress two atoms so that the electrons and protons are right up next to the nucleus. And that way the center, from the center to the center, the atoms can get a whole lot closer together. Now that's up for grabs on which one of those it would be, because I don't know if you can compress an atom so that the electrons and protons are right up against the nucleus. That might not be possible. But anyway, that's where I came up with that, because it's just that there was no, I never seen anything with relativity where they account for a black hole. They might have something that accounts for it, but I've never seen it before. But anyway, that's about all I can think of for that. Yeah, there's probably something that I forgot, but that's about it in a nutshell. That's quantum gravity, which actually I think that, I mean, I'd have to leave it up to them, but this might qualify as this unified theory they're looking for. Of course, I know what they've been looking for is something that will unify relativity with quantum mechanics. Well, I just don't think that's possible. That's not going to happen. It's a square peg in a round hole. But anyway, this would be a theory of gravity that would agree with quantum mechanics, because it's loosely based on quantum mechanics, because it's based on atoms. And another possibility would be that, since apparently they're, from what I see on how the universe works, they're looking for a substance called dark matter. That apparently, from what I gather, they're trying to explain how we can have so much gravity with a limited amount of mass. There's not enough mass to account for the gravity. So they think there must be some dark matter out there that's creating all this extra gravity. Well, now if they take into account the mass density coefficient of black holes, because a black hole can have a limited amount of mass, but it can have an enormous amount of gravity in proportion to the amount of mass there is. So there's your extra gravity right there. So if they account for that, for the large number of black holes that are in the universe, there's all your extra gravity. They might not need to find dark matter. I mean, I have to leave that up to them. I don't know anything about that. But anyway, that's a possibility. But that's it in a nutshell. So that's it for quantum gravity. So now my next video is where I'm going to disassemble general relativity, because it doesn't cause gravity. I can prove that. Anyway, I hope to see you there.